amperes.
Yes.
So you said volts, seconds per Henry.
Yep.
So Henry volts is another unit of time, right?
You lost an ampere in there.
Oh, okay.
It'd be an ampere Henry per volt.
Yeah, ampere.
So I sub L is going to be 18. Is it 18?
Yeah. 18.75.
All right. I'm just going to put a little make that. Oh wait, that's going the wrong way.
Why do we not like it?
I want it to be in the same ballpark as the other ones. So I'm going to make this 200 millihenries. Make this 0.2 to make this 1.8. So 1.87577 amperes times the cosine of 376.991 times time plus pi over 2.
Minus 5.
Thank you. Minus pi over 2. All right, we've got one last thing to do. We need to get the power supply, the current from the power supply. I know that in this situation, based on what we've done here, well, actually, I sub L is bigger than I sub C, so we went the correct direction here. I know that is lagging behind my voltage phasors because I sub L is bigger than I sub C. And I need to figure out by how much. What is this angle right there? Well, I can find that angle because, yeah. And this is basically what I'm working with here. This is I sub R. This is I sub L minus I sub C. And that's the angle I want to figure out. Well, so I know that I'm going to use tangent, that's my right angle there. Yeah. So phi is the arctan of I sub L 1.87577 minus I sub C, which is 1.59919, divided by I sub R, which is 2.356 we end up with a phase angle of I guess it's somewhere around 0.14. What is it? Second up to the plate is around.
Yeah.
All right. Do it.
0.117.
0.117
Yeah.
units?
Degrees, radians.
Radians. So I'm not going to write it. Therefore, I for the power supply is, oh, we actually don't have big I yet for the power supply. I know that big I for the power supply is equal to epsilon sub naught over the impedance. Epsilon sub naught I erased, but it is written there, that's 141.4 divided by, and the impedance, well, we got the formula right over here. Right there. 1 over the square root of R squared, that's 60 squared, plus 1 over omega L. Wait, it's 1 over R squared. So 1 over 60 squared plus 1 over the x sub L, which we've got, so there's an X and an L. Minus X sub, minus 1 over X sub C. That's squared. And what do we end up with for our, first, what is the impedance, the number? Now, see more than one calculator out, but a lot of people stay in silent, so just go for it. What did anyone get for Z?
Working on it.
I got 59.59.
For Z,
Yeah.
59 point what?
59.
So we got 141.4 divided by 59.9, which is 2 point something.
Where's the decimal? On the 595. What?
I don't know what's going on, but 2.37.
2.37?
There's a bunch of numbers.
So this is 2.37 and a bunch of numbers. And a bunch of numbers. Amperes times the cosine of 376.991 radians per second times time minus 0.117. So, how can we test this? How do we know if we have done something right?
If all the. If all the currents.
Pardon? Plug your jug. Let's plug your jug. Let's just we'll take a simple case here of time is equal to 0. Boring, but so at time is equal to 0, we have the current from the power supply is going to be 237, and I believe kids today write 2 that way. 2.37 cosine of negative 0.117. The current across the resistor is 2.35, did it again. .356 repeating. The current across the capacitor is going to be 1.59919 times the cosine of pi over 2. And the current across the inductor is going to be 1.8757 times the cosine of negative pi over 2. So the first one should be about 2.35,
That's also a 3.
2 point, wow. 2.356 repeating, I assume.
It's just 2.53, or 2.354.
Okay. And these are both equal to 0. Which is why this is a boring case. But what we are showing here, or what our check is, I know I have current coming out of my power supply and it is going to split. So the current going across the resistor plus the current going across the capacitor plus the current going across the inductor should add up to the current coming out of the power supply. And it should work for any time. The instantaneous values obey Kirchhoff's rules. The amplitude obeys Ohm's rules.
So, where does the 0 fit in? Like right after like the pi over 2t negative pi over t. No, negative.
I guess the question that you actually started with,
I was saying, where do you put the t equals 0 in? But it's just right after the things in parentheses. Over there.
over there,
Yeah.
oh, well, I put 0, when time is equal to 0, I'm gonna put that in for t here.
Yeah.
But the fact that they come out, now there's some rounding differences here, but the fact they come out that close tells us that something has gone right. A better test would be to pick, say, 0.01 seconds or something like that. But that will be for another day, because I think class ended 10 minutes ago. No, only 8 minutes ago. But Mars Lab, I'm sorry, there will not be an inductor Mars Lab.
Why?
Because that is reserved for the following week.
Will it be posted with Blackboard?
Say it again?
Is it on Blackboard?
Don't think so, not yet, but, till noon.
Is there a problem with like series and parallel? Is there a problem with like series and parallel?
Oh, that has a combination? Just give you a sneak preview of Wednesday. Here's the power supply, let's stick, say, a resistor right here, and then a parallel structure of an inductor and a capacitor. Good stuff.
Was that one of the longer ones that we'll do, or is that pretty average for all of these?
This one?
No, that one.
That's pretty standard. This one is. This one would be a challenge.
Now, this is like for sure we're gonna see on the test, right?
It's definitely fair game.
Word. Capsies.
Oh, last week's? Well, I'm stopping this.